Hello everyone, I'm Wei-Fu Tseng. The title of the talk is Online Learning of Quantum State with Logarithmic Laws via VB-FTRL. And this is the joint work with Kai-Chun, Tseng, and Yen-Huan. Our research problem is a specific problem called Online Learning of Quantum State with Logarithmic Laws. The problem is formulated as a sequential game between two players, learner and reality. In each round, first the learner announces a quantum state described by a density matrix. The definition of the density matrix is below. A density matrix is a Hermitian and positive semi-definite matrix having unit trace. Then the reality announces a Hermitian and positive semi-definite matrix. Finally, the learner suffers a loss, which is the negative logarithm of the trace. And in this game, we will act as the learner, and our goal is to minimize the regret. And there's an interpretation of our problem as the probability forecasting problem. And where does the problem? And to know where the probability comes from, first we need to know an operation called measurement. A measurement is represented by a POVN. A POVN is a set of Hermitian and positive semi-definite matrices that sums up to the identity matrix. With a POVN, we can do measurement to a quantum state. The measurement outcome is a random variable, and the probability distribution is given by the trace. And here comes the probability. Yeah. And now, if the Hermitian and positive definite matrix AT was given at the versoriality from the POVN, the trace represents the probability. So, minimize the loss function can be interpreted as predicting the measurement outcome with highest probability. And our problem is not only just a theoretical online learning problem, and it has at least two applications. And the first one is the maximum likelihood quantum state tomography. This is a task in quantum information theory. And the second application is to approximate the permanent of a Hermitian and positive semi-definite matrix. It's a computational problem. Consider a special case that all the matrices are diagonal. In this case, we can express the diagonal matrix by their diagonal elements. A density matrix can be expressed by a probability vector. Then a Hermitian and positive matrix can be expressed by a non-negative vector. And it turns out that this special case is an classical online learning problem called online portfolio selection. And there are the works on these two problems are related, including our works. And to understand our work, we need to know more about online portfolio selection. The online portfolio selection is proposed by Thomas Covert, a famous information theorist, and designing an efficient algorithm that is optimal in regret has been an open problem since 1991, and until 2020, it was still an open problem in code. There are many algorithms for online portfolio selection, and I presented the best of them and in terms of the per round time and regret. And
I think you are in the wrong page, the previous page.
Yes. Oh, yes. Of course, we prefer algorithms that has both a low regret rate and low per-round time. But currently, there is no algorithm can be optimal in both these directions. And among these algorithms, we are particularly interested in two algorithms. The exponential weight method already achieves the optimal regret rate, d log t, but its computational time is very high. And in comparison, the VB-FTRL is the first algorithm that achieves the optimal regret rate with low computational complexity. Our work generalized the VB-FTRL algorithm to the online learning of quantum states with logarithmic laws. And similarly, we compare our work with other works in terms of the per-round time and the regret rate. A direct generalization of exponential weight method achieves the best known regret rate, which is d squared log t. However, it's computational. However, there is no implementation of this algorithm. Our work generalizes the VB-FTRL algorithm and achieves the best known regret rate, d squared log t, while runs in polynomial time. Now I explain what is the VB-FTRL algorithm and how we do the quantum generalization. The VB-FTRL is a further regularized leader type algorithm. The VB stands for the volumetric barrier. For any strictly convex function phi, the associated volumetric barrier is defined as the composition of the log D function and the Hessian of phi. In our quantum generalizations, there are two main differences. And first, we replace the logarithmic barrier by the log D function. And the log D function is the direct generalization of the logarithmic barrier. The second difference is concerns the Hessian of the function LT. And it is a function that has matrix domain. And on the other hand, the Hessian of a function is also a matrix. It is not clear how to define a matrix of a matrix, so we do a vectorized version. We do a vectorization to the function LT. Then this enables us to convert the matrix domain into a vector domain. Although our generalization is straightforward, the challenges in our work is how to analyze the generalized algorithm. There are two challenges in our work. The first one is the affine reparametrization step, which will be defined later. The second challenge is how to verify the convexity of the volumetric barrier. And note that we cannot directly apply existing result to resolve these challenges. And now I will provide details of these challenges respectively. The first challenge is the affine reparametrization step. And the affine reparametrization works with a special class of function called self-concordant functions. The precise definition of self-concordant functions is not needed to understand the talk. And we just need to know that those functions and regularizers are self-concordant functions. To apply existing results to apply existing results on self-concordant functions, we require these functions to be barriers. However, the logarithmic barrier is not a barrier for the probability simplex. So in the original work of VB-FTRL, they introduced an affine reparametrization for the probability simplex. However, this reparametrization cannot be directly generalized for the set of density matrices. And this is our first challenge. To address these challenges, we apply a strengthened version of existing result updated from a result of Tseng. And the lemma states that for any self-concordant functions, we can give an upper bound to the difference between the function value and its minima. And if we further assume that f is a barrier for its domain, it is a standard result due to Nassroth. And in the original work of VB-FTRL, they apply this result directly. And however, in this lemma, we can remove the assumption, and it allows us to bypass the reparametrization step. And the second challenge is how to verify the convexity of the volumetric barrier. In VB-FTRL, the volumetric barrier is defined associated with the regularized cumulative loss, LT. And the convexity of this function is required in the regret analysis. In classical case, the calculation can be the calculation verifying this property can be done explicitly, and there are some existing results can be directly applied. However, in a quantum generalization, the calculation appears to be complex and challenging. And to address these challenges, our approach is to propose a notion called VB convexity.
Maybe let's take 1 or 2 minutes.
Yes. A convex of the VB convexity is a condition on the directional derivatives of a function, and we in our paper we prove a theorem that for any VB convex function, the associated volumetric barrier is always convex. And so the VB convexity is a sufficient condition for the volumetric barrier being convex. And in our case, the remaining question is how to verify the VB convexity of the regularized cumulative loss. And we prove it by applying the following lemma. Roughly speaking, the VB convexity is closed under additions. And the rigorous lemma is that for any two VB convex function, phi1 and phi2, their weighted sum is always a VB convex function. So to verify the VB convexity of the regularized cumulative loss, it serves to verify the VB convexity of both the loss functions and the log D functions independently.
Having wrapping down slides.
Yes. Oh, can I change the slide page? Sorry. switch to the next page. I summarize our work and provide some directions for future works. We generalize the VB-FTRL algorithm to online learning of quantum state with logarithmic laws and achieves the best known regret d squared log t. The minimax regret for this function problem remains unknown. If we can prove the minimax regret is also d squared log t, this can establish the optimality of our algorithms. And in our work, we also verify the convexity of the volumetric barrier by proposing a notion called VB convexity. And in the original work of VB-FTRL, the volumetric barrier was known to be self-concordant. And if we can prove that in a quantum generalization, the volumetric barrier is also self-concordant, and it may lead to a faster implementation of VB-FTRL. And thank you, everyone.
About what is the fastest that this VB-FTRL algorithm can be implemented in? Maybe not the quantum version, but the regular version. It's like there's some nice curve, right, that you're showing. Trade-off between speed versus regret.
Yeah.
Do you have any intuition about what is the most leftmost that we could get?
Left? In the original work of VB-FTRL, then they provide an intuition of the VB-FTRL, and they prove that VB-FTRL can be interpreted as an approximation of the exponential wave method by truncated Gaussian distribution. Yes, and so I think to achieve the best optimal regret d log t, we may start from approximating the exponential wave method.